All right, so we're going to review total internal reflection today. You can see a picture of me and Miss Chan here. And in this picture, we actually see an example of total internal reflection, and you'll understand why after this video. So remember that refraction is caused by the change in speed of light as it travels from one material to another. The speed of light depends on the optical density of that material. So the more optically dense the material is, the slower that light travels through it. So for example here, when we have a beam of light traveling from air to water, it's going to bend towards the normal. So we have it coming in, bending towards closer to this normal here, because light is slower in water than in air. The rules of refraction are that light bends towards the normal when light is slower than the new medium. Light bends away from the normal when light is faster in the new medium. The incident ray, the refracted ray, and the normal all lie in the same plane. Okay, so we know that when we have something that's going faster, we're going away from the normal, and slower, we're going towards the normal. Okay, so here we have a situation where we're going from water into air. Okay, we know that we have a index of refraction of 1.33 from water, and air has an index of refraction of 1. The speed of light increases at the boundary, causing light to bend away from the normal because it's moving faster. So the angle of refraction will always be larger than the angle of incidence. Here's a situation where we can start to talk about total internal reflection. As the angle of incidence increases, the angle of refraction increases as well. When the angle of refraction increases to become 90 degrees, the angle is called the critical angle. So here, this is an example of refraction. Here, we have our incident ray coming in, and the reflected ray is right on the normal. That's called our critical angle. The critical angle is a physical property of a medium, so all different mediums will have a critical angle value. If the angle of incidence is increased past the critical angle, the refracted angle will not exit the medium, and all incident light will reflect back off a boundary into the medium. So if you think about that first image we saw that picture of the turtle on the top. That's because we had total internal reflection, and we had a reflection off the water. So this will only occur at a large angle of incidence that's greater than the critical angle. Okay, so like this fish here, we can see the reflection because when we're going from water to air, we can have total internal reflection. This takes place when both of the conditions are met. So number one, light needs to travel slowly in the first medium than the second, and the angle of incidence is large enough that no refraction occurs in the second medium. Instead, it's reflected back to the first medium. The angle of incidence is greater than the critical angle. Okay, so we have these three examples here. Water has a critical angle of 48.8 degrees. If the angle is less, we have partial reflection, so that's this dotted line here. If it's at the critical angle, we'll still have partial reflection. And if it's past the critical angle, we will have total internal reflection. So now I want to challenge you to research how does total internal reflection relate to diamonds, fiber optics, and triangular prisms. Thank you for watching.